Okay, so here's another a second example of differences between Linux and well, GNU-C and ANSYS. Um, there are these directives, built-in directives. There are many of them, but likely and unlikely are two directives that you will see a lot in the Linux kernel code. These are built-in directives that optimizes conditional branches uh, as either something that is very likely taken or very unlikely taken. So, can you think of a reason why they would do such a thing? Okay. I'm not going to put questions on this lecture for multiple reasons, but the main reason that they are doing that is that this is a very nice optimization in the kernel. In normal if-else statements, I mean, if you do not tell, in normal if-else statements in most programming languages, you do not have a way telling the compiler that, well, the if-else statement here stands for if Earth gets split into two halves, then we should play this kind of sound, for example. I mean, maybe you have such a thing, or if sorry, okay, sorry. Um, yeah, if something that is very unlikely to happen uh, happens, then the compiler basically has no way of knowing if this is likely or this is unlikely. And GNU-C, since in the operating system you really want to optimize to the very last cycle, you really want to optimize to the very last 1 nanosecond or microsecond. You want to basically save any wrong branches that you take, any probability of wrong branches that you take. So one way to do that is that, for example, it's in the unlikely case that a memory segmentation fault error happens, do something. In the likely case that boot occurs, so for example, if you're doing the boot, in the likely case that boot is successful, then do the following. I mean, almost every time you start your computer, your boot will be successful. There are very unlikely cases where your boot will fail because of anything. I mean, I cannot remember of a single time that my boot failed due to a software or operating system's error. But you probably, I mean, of course, if the hardware breaks, it breaks. But otherwise, in most cases, if Linux is starting, then it wouldn't really break in the middle of the start. Very unlikely. But in these unlikely cases, you want to do something. And then the likely cases where boot actually occurs, you want to do something different. So you're basically telling the compiler that, well, this is a very high probability thing. Go on and fetch the next commands for that come after this. And this is an example from the work queue. It's basically um, what happens if you have an empty list of operations to operate on. So if you're basically you have work queue, which basically has all the processes, all the different things that need to be run on the scheduler, by the scheduler on the CPU. So you have this work queue. Suppose that in the unlikely case that this list is empty, you need to do something. In the unlikely case that you do not have anything to do, you need to do something. As I said, there are no memory protections in the kernel, which basically means when a user space application attempts an illegal memory access, the kernel traps an error and it sends you a sig v signal and kills the process. It's basically a fault, right? It's one type of fault. It's there are these signals that the kernel can send, and the signal is basically if and a signal is typically, so you have a syscall that goes from the user space to the kernel space, right? So you're basically syscall is basically you at the user space trying to do something, and you send it to the kernel. Signals are the exact opposite. So you're going from the kernel space to the user space. So when such a thing happens in user space, so you're running your program and you try to access an illegal memory, the kernel will basically send to the user space that, oh, there is this error, and it will kill the process right away. Versus when the kernel attempts an illegal memory access, you get something that's called whoops, and you will be seeing a few whoopses in your kernel development if you choose to do these two projects. So yes, you get a whoops, OOPS. Okay, and this is basically the kernel will crash. Depending on where this happens, you might end up with a kernel crashing and you needing you in need of reinstalling the kernel, or reinstalling your virtual machine basically. In most cases it wouldn't, because in most cases we're going to be working very far away from anything that is central, so you'll probably be safe. But in other cases you might get you might need to reinstall the virtual box basically, and this is why we said you need to have some virtualization to run on, because otherwise if you do that on your computer, well, too bad, you need to reinstall your whole operating system now. And I'm hoping that you only get whoopses in when you're doing non-central things, so that you can actually start the virtual machine and just change that code. And this is an example where whoops will be thrown. This is actually from inside the kernel. There is a file that's called fault.c, which basically handles kernel faults. You see this function do kernel fault, which handles whatever happens in the kernel. And you see that there is die, whoops, and then some other arguments. But yeah, you get the idea of what die will do, right? I think its name is telling. Floating point operations. The question is, why would you do that in the kernel? It's generally horrible idea, because, well, I mean, operating floating point operations are very hard. You really, they take time, and so on and so forth. And floating point operations in user space, you usually have the kernel actually handling them by having a trap basically that initiates the transition from integer to floating point mode, and that basically is meaningless if you do not know what the architecture is, because some architectures will support floating point operations in the hardware, others will not, and depending on what architecture you're running on, your floating point mode will vary, the meaning will vary. Using a floating point inside the kernel requires you manually saving and restoring floating point registers, which is a real pain, and it takes a long time, and you want your kernel to be blazing fast, right? So the Linux kernel stack size is in general very small and fixed. We talk about it in more details later, so we are just going to skip that. With this was our primer on a few things to note when doing kernel programming. I will the next lecture will be basically a continuation on what happens with processes. I mean, it will be half theory and half kernel. So I will try to record it over the weekend, so I would expect that you will get the lecture, the next lecture pretty soon. The lecture that I'm planning to re-record, the first 4 videos that I'm planning to re-record, I'm actually going to re-record them hopefully tonight. I'm still, as I said, suffering from my trip, and I know that it's no fault of yours. I just didn't want to cancel the lectures when we have just started, and I have posted the midterm times. I will post not the syllabus but the schedule, where we're basically saying when we will release the different projects and when we expect them, so that you guys can also plan for that. I'm really sorry about this. It's just been 2 months of constant traveling and jumping. Thank you, and I will see you soon, but I will also hopefully see you all on next Thursday.